And then you go to starting point. The first one was brother big.
Okay, ladies and gentlemen. I'm going to start with you. What's the difference between a process and a program? Anybody knows what the difference between a process and a program is?
A process is a program in execution.
A process is a program in execution. And what's a program? Is a program a hardware? What is it?
So,
Piece of software stored on it.
Anybody there? I hear somebody talking here.
It's a piece of software that's stored locally on it.
Yeah. It's a program is a list of instructions. It's a static list. It's doing nothing. It's stored in a file, saved on a hard disk or some storage device. But it's doing nothing. It's only when we pick it up and we put it in memory and we start running it, we start calling it a process. Right. What's a kernel? Anybody know what a kernel is? Yeah? The what?
Like the most basic type of software that we have that contains like basic how to read.
It's an essential. Yo, please guys, either listen to us or so. The kernel is the essential part of the operating system, the most important part. The part is without which maybe operation will not continue successfully. The operating system consists of two parts. The essential part that must be there on the machine in main memory, running and ready when the computer is switched on. The rest of it, the non-kernel part, are the parts that are also part of the operating system, but maybe we don't need them all the time. So they are stored somewhere else on a hard disk. And if we need them, we bring them in temporarily, just like any other program, run it, and then get rid of it again. Move it off more. What's a microcomputer? A microcomputer. It's a multi-user computer. Are we there yet? So he said, what did he say? What's a microcomputer? He said it's a multi-user computer. Pardon? It's a personal computer. It's one user only. This computer. What about the mini computer? Which one is bigger, the mini or the microcomputer? The mini computer. How many users? Approximately. 2 or 20 or 200. Okay. Or 2,000. Yeah, 20. Good choice, good selection. Right, so a mini computer is like a mainframe but reduced in size, reduced in cost as well. So if you are asked to compare two types of computer hardware, mainframe, mini computers, microcomputers. Mainframe is the biggest, the most expensive, the most powerful, and then reduced in size and number of users as well. Now, mainframe has large number of users. Mini computer has smaller number of computers, it's smaller in price, and then the microcomputer is the smallest of all. That's like a desktop or a laptop.
So have you started recording? Have you started recording it?
I have, yes. Processing, the different types of processing. We have a batch processing and we have interactive processing. What's the difference between them? Give me one difference.
Batch processing would take any programs to process that one.
So batch processing takes a group of programs or processes to process later. Which one, what's the difference in response time between batch processing and interactive processing? Yeah? So interactive has a quicker response time. Okay, interactive, what's response time? What's response time? This hand. Anybody can tell me what response time is? Describe it, you don't have to give me the exact definition. No, okay, what does it mean? If we say response time is 2 milliseconds, what do we mean by that? Okay, time taken by the computer to react to a request. And what's turnaround time? The total time from placing a request until all the command has been done, whatever it is. And I always use an example. I say, print the list of all the names of all the books. So the moment you hit that request and you see the first name appearing, that's called response. How long does it take for it to respond to you? You see some sign that the computer is working for your request. But then you start seeing the list keep going and going and going. Then when the last name is finished, is displayed, and the program is completed, that we call that turnaround time. And we will be using a lot those two, response time and turnaround time. So you need to know what they are. Turnaround time is from the time you go into a place until the time you leave it. So if you go to McDonald's, say from the moment you walk into the door, and then you start looking and ordering, making up your mind, I don't want this drink, and then eventually you place the order and wait, and this is a takeaway one. And then they put it in a bag, and the moment you walk out the door, that's turnaround time. It could be the same for a car going to fill petrol in a petrol station. From the moment it drives into the garage or the petrol station, and it might have to queue behind 2 or 3 cars, and then when it gets to its time of service, the time it fills, time to pay, and then leave it. That's called turnaround time. It does nothing. It includes waiting time and actual processing time. And the same in computers. If you ask to run or execute a program, it's not always running. Most of the time, programs are waiting for something, waiting for an input to be read or an output to be generated and sent out. In fact, not a lot of time is used for processing. Now, what's a CPU-bound program or an I/O-bound program? Did we mention this? Okay, anybody wants to have a guess?
Program that's on its way to the CPU.
Yeah, every program will need the CPU to run, but sooner or later, it's gonna stop and it's gonna need an input or an output. Remember, if you ever write a program that does not ever need any input from a file or from a user, from a keyboard, from anywhere, then it's a useless program. Don't write it. Don't say I wrote that program, because that program will be doing the same thing all the time, producing. Let's say you say print x equal 25, print x, it will always be printing it, because your program never takes any input to change that value. So every program, every process that runs will need some input, and it will also need to produce something, and it will need some output. Again, if you write a program that produces nothing or displays nothing on the screen or does not send nothing to the printer or nothing to the communication line, it's even worse program than the one that doesn't take input. So it's another useless program. So this is the nature of all programs in computers. They must take some input and they must produce some output. And while they are taking the input or sending the output, they don't need the CPU. Right? So your program is either using the CPU or wants to use the CPU if it was available, or it doesn't need the CPU and it needs some input or output. Input or output like hard disk, maybe of reading a file or writing to a file or reading off a keyboard or sending information to the communication line or reading a scanner or a camera. That's all that is input and output. While it's doing the input and output, it doesn't need the CPU. So your program and every program will spend some time using the CPU, sometimes intermittently. So it runs the CPU a little bit and then reads some information, gets the CPU a little bit and print the processing it done, and then ask for more input. So it needs the CPU, so it goes into cycles. Every program goes into CPU cycles and I/O cycles. Now, programs can be classified before you leave. Just wait, when we get to the punchline, you decide to leave. The last 10 minutes are just an introduction. So now, if your program needs a lot of CPU time, some programs need a lot of CPU time. Example of that, if you say, for example, in a month from now, on the 3rd of whatever, March, is it gonna rain or is it a dry day? A real scientific program that goes out through all the weather forecast, all the previous history, and all the input and humidity and temperatures and wind speeds, and calculates all this in a big model, big mathematical model. We'll do a lot of processing. It will need the CPU maybe for 5 or 10 minutes, doing a lot of processing, maybe even more. And then it produces one word, rain, and that's all it does. So this kind of program uses a lot of CPU, very little I/O. And we call this kind of program CPU bound. So CPU bound programs are programs that need a lot of CPU, a lot of processing, and very little I/O. On the other hand, there are other programs that they have different nature. For example, if I say print the names of all the students, no processing, you don't have to do nothing. Just get the names from a file on the hard disk. So your computer is going to work like this. Get me the CPU, got the CPU, start running, open the file. While the file is being opened, it doesn't do anything. It doesn't need the CPU. Now, read me one record from that file. So it reads one record. While it was reading the record, it doesn't need the CPU, so it leaves the CPU. It doesn't need much processing. Let's say send it to the printer and wait for it to print. So most of the time, and then when it prints, when we tell it we finished printing that record, say, right, get me the second record, the next record of the file. So it's waiting. Most of the time, it's either reading or sending to the printer with no or little processing in between. We call this kind of program I/O bound program. So it's an I/O bound program is a program that needs a lot of input or output. And sometimes some books, they say longer I/O cycles, because you don't just have one long I/O. You always read few records, write, get the CPU a little bit, read more records, get the CPU, print, and so on. So there are always few instructions in between that need the CPU. But in general, if it uses a lot of I/O time and very little CPU time, we call it I/O bound program. And how important is this, or how good is this? Or what difference does it make whether we know our programs are I/O bound or CPU bound? It's like this. It's like, for example, if we decide we all go somewhere to one of these games places, and they have snooker tables or pool tables, and they have table tennis. They have 6 of those and 6 of those. Now, if we all go as a group, and every one of us hate table tennis, right? Everybody wants to play pool. Guess what happens? Those resources, the 6 tables that are sitting there, they're going to be nobody using them, and every one of us will be queuing up to play pool, waiting for those who are playing to finish with the next person. Operating system, what it does, it needs to find out when 50 programs arrive for execution, it needs to decide quickly, or if it knows already, which ones are CPU bound, which ones need CPU, and which ones need more I/O. and it tries to pick one of each and send them into the system together. So when they walk in, one of them is happily playing with the CPU or using the CPU, the other one is happily reading an I/O. And every now and again, each one of them will swap a little bit. The CPU bound will need a bit of I/O, and the I/O bound will need a bit of CPU. So the point is, if half of us wanted to play pool and the other half wanted to play table tennis, and we go in, then the 6 pool tables will be used, the 6 table tennis will be used, we're all happy playing and nobody is waiting. So it's important to know what nature of these programs are later on. So for efficiency, for more utilization of the resources that are there, if you have resources, you want them to be used as much as possible. And also you want to reduce the waiting time or the turnaround time for all programs. You don't want every program waiting, they're all waiting on one file or one CPU, and nobody wants the rest of the resources. So that's the point where operating systems, they always want to know whether this is an I/O bound or a CPU bound process and the difference between them. And the point is they try to mix them. Going into the system, they try not to send 50 programs that they all want the CPU. Then the input-output devices will be sitting idle, nobody's using them, and all those 50 programs will be waiting in a long line, waiting on a CPU. That's not a great way to run the system. So that's one of the things that the operating system does. Any other questions on what we've done so far? Now, what's the difference between interactive system and real-time system? Go. Real-time system is faster. Okay, interactive systems are pretty fast too. And it's better than using the word faster, use the short response time. They have short response time, quick. You know, when you type something, you get quick response. Interactive systems are called interactive because people or programs are using it, and people get bored if you type something and you wait for it, it doesn't come back in a few seconds. You say, wait a bit longer, you probably will never wait for a minute. You say, leave that, you know. All right, so that's interactive systems. Interactive systems are systems normally that are used by users and they need very short response. So if it's long response time, it becomes like batch systems. Batch systems is a system that you submit a request and it will be processed later. We don't know even how long it's going to be. It can be minutes, can be hours, can be days. That's called batch processing system. And the way they do it in batch processing, they collect a group of them together to execute, but not necessarily. But the sure thing about batch system, they are not interactive. You give the program to run, and most programs, they probably come back to you and say, okay, what's your name, or what do you want to do, or give us a number. No, batch systems, they don't have interactive applications. You give it, they'll run it, and it will finish the job without asking any more questions. It might read from files as input and all that, but not from users. It's like a backup file. You might have a batch system. An example of batch system is a backup file, where you say, listen, at 12 o'clock, back up all my files, copy all the files on my disk, and put them somewhere else on another hard disk. Now it doesn't come back and ask you, well, listen, what do you want to name this file or anything? No question. Just go and open the hard disk and open each file, read from it, and write it onto another hard disk. So that's called batch system. Interactive system are systems that will exchange information with the user. Some user, it could be a program, but it could be most likely it's a person. And people, they want to kind of have a quick response. So interactive systems are systems that also have short response time. So that's not a major difference between response time and real-time system. Anybody else can tell me another difference between interactive systems and real-time systems? Anybody? Hands up?
The real time is like most of the time it's 100% efficient, but the interactive, it could be 80%.
Exactly. So most systems that we are using in the world today are interactive systems. You get in, you want to see a website, you type in website, you get response within a second, it's displayed on your screen. That's great. That's called interactive system. But sometimes it takes 10 seconds, occasionally. That's okay. Interactive systems, they have short response time, but sometimes they don't. Most of the time they do, of course. But real-time systems, these are the kind of systems that are guaranteed to have a short response time, 100% of the time, always. We do not allow a system to have a long response time or delay, or else, some major issue, major problem will take place. So always think of it like maybe flying a spaceship or an aircraft, flying an airplane with passengers, and you're sitting at home flying it. In 20 years, pilots probably won't be needed on airplanes. Probably airplanes will be flying on their own. But imagine if they said, no, but we need somebody standby sitting there at home, but they can take control over the airplane. So you're flying an airplane, you go down towards a mountain and you want to pull up. You don't want the system to break at that point. You want a quick response. This is called real time. So real-time operating systems are systems that require very short, very quick response time all the time, without fail, without any delay. Interactive, they also require short response time, but sometimes it's not necessarily that they have to be 100%. We can put up with a slight bit of delay. What about batch systems? How much response time? Do they have a shorter one? Batch systems, batch processing systems. Okay, I'll come back to you. Batch operating systems.
You can never know.
Pardon?
You can never know.
Well, that's probably maybe with interactive systems. What about batch systems? What would you expect? Guys, could somebody tell us what a batch system is? Let everybody know. So listen, guys, this is the reason why I ask questions. So if you don't know, okay, it's good now that you don't know now, but hopefully you should know. And I'll keep asking you again until the exam day when it comes in, and you'll find in the exam, what's a batch system? You say, oh, I remember that because I was asked many times. Right, hopefully. So do you know what a batch system is? Can you tell us? Can anybody tell me? Who can tell us what a batch system is?
A batch system is a system that does that it compiles the file before it gives the response. So with that, it takes longer time than the real-time and interactive.
Exactly. Right. I'll put it in shorter words. A batch system. You put in a request now, it will be processed later. Definitely later, not immediately. So the response time, according to that, it's going to have a long response time. Definitely. Every batch system will have long response time. It doesn't work in seconds or milliseconds or millionths of a second. It works on minutes or hours or even days sometimes. An example of batch system, I say, do my backup tonight. So you issue the request now, but it's not going to happen now. It's going to happen tonight, maybe at 12 o'clock. You decide what time you want to start, maybe, and it will start doing the backup of operation. That's called batch processing. And the main feature of batch processing, what's the main difference between batch processing and interactive processing? Yeah, response time is much, that's the major difference. Interactive systems have short response time. Batch processing systems have long response time. Okay. What else are we going to talk about? So today we're going to be talking about memory. We'll talk about memory manager. I don't know. Is it better this way without? We'll see how we go. Right, so we're going to talk about memory manager. Can you see the writing here? And see the difference between this and the same writing now. You need, probably there's no difference, is there? Okay. Okay. The memory manager. Who's going to tell me what are the responsibilities of a memory manager? Give me one responsibility of a memory manager.
Manage the memory.
Say again?
Manage the memory.
It manages the resource, which is main memory. Anything else?
Allocate and reallocate.
Thank you. That's the easiest one. Allocate and deallocate. Every manager will allocate and deallocate. What will this one allocate? Memory. So it will allocate memory to programs or processes. What's the difference between a program and a process? Okay, what's the difference? I asked this 10, 15 minutes ago, guys. A program is what? Yeah, a program. A program is a list of instructions, guys. Yes. And a process? Education, yeah. It's a process is a program in execution. Yeah. So that's the difference. A process is also a program, but it's running. It has memory, it's put in the CPU, and it's getting CPU and waiting and all that. So it's a dynamic thing. It's a living thing kind of thing. A program is just stored on a hard disk. Like a program is like a book in a library sitting somewhere. It's useless until you go get it, move it to your brain, your mind, and then start hopefully applying it. Right. Memory is technologically was difficult. First, there was very little memory before the 60s. And then transistors were introduced. And a transistor memory is just a switch that's on or off. That's all a computer really knows. And that's the basic operation and intelligence of a computer. That it can look at an electric switch and says that electric switch is on or it's off. And it's probably connected to a lamp. And when it's bright, we can tell it's on. And when you hit the switch off, the light goes off, and then we say it's open. But pretty much the same idea that how a computer identifies a switch, whether it's on or off. And the switches used to be quite big, and they consume a lot of electric power, and they become very hot. Computers in the old days, they needed air conditioning systems in the room, and they were so big. When transistors were introduced, and what a transistor is a tiny switch. And lots of those small, tiny why we call them electronic switches now. But they're just basically an electric switch that can be put on, switched on, or switched off. And a computer can tell whether it's on or off very easily, very quickly. And it consumes very little electric power, but it needs very little power to run it. And it doesn't generate that much heat. Very little heat. So it's a huge development in computing. That's really one of the biggest developments that ever happened in the history of computing, the introduction or invention of transistors. They reduced all electric and electronic equipment into tiny things. So now instead of having a radio that size, now we have radios that size and even smaller. And instead of needing a room like this to have memory switches, now we need 1 square centimeter on a small cell, and can have millions or billions of electronic switches. So that's what memory is. But in the old days, it wasn't available, and still not abundantly available either. And therefore, and the other thing about it is every program you need to execute, it must sit in this memory. It cannot sit on a hard disk. And at that time, there weren't even hard disks. There were no such thing as hard disks. They were a newer invention. But they were tapes. But you can't have a program list sitting on a hard disk or a tape and execute it. Because when you want to execute it, the way programs are executed, you take one instruction at a time. The way computers work are like this. The way instructions are executed. You probably already know this. If this was memory and you put a computer program in memory, in order to execute this program, you also have on the same motherboard, you have something called the CPU. That's the intelligent part that actually will execute instructions. It's like the brain in us, in human beings. They know how to answer questions. But the CPU can only answer 256 questions. That's all it can do. In some computers, 512 instructions. That's all really a computer can execute intelligently. That's what the CPU can do. And also, in order to do this, you must get one line of code, one instruction moved into the CPU. So CPU is like a factory, in a factory, like a machine, and all the instructions coming in one at a time, like a factory line coming in. Imagine, I don't know what it is, you have a chocolate coming in, right? And then it comes into a mold and there's a big hammer, boom, it's done. That's what the CPU does. Get the next one, boom, and executes it and goes. So the CPU gets those commands one at a time, execute each one. The only good thing is that it executes 1 million of those instructions every second. That's how fast it does. So it gets the first one in, executes it, get the next line, execute a third one, fourth, and keeps just, it doesn't know which one it should be executed, just say, get me the next one. The operating system will be passing those, or the programmer will say, okay, go back to line number 500, go back, so somebody will, it will actually execute this instruction, go back to line 500. And then there's a mechanism that feeds in those lines one at a time, in 1/1000th of a second, each one of them, and gets executed. So that's what the CPU does. That's why we need to have electronic memory that works so fast to give those lines. If the program was sitting on a hard disk, you cannot move information on a hard disk at a speed of 1 million lines per second, because hard disks are mechanical devices. And mechanical devices are so slow compared to the electronic devices. Electrons flow through the electric circuit or electronic circuit through wires and metals at a speed that's 0.8 of the speed of light. So things move so fast electronically. That's why we can execute 1 million instructions every second. But if it was on a hard disk, we couldn't do it. So main memory is so important to have, or else really there'll be very little computing or very slow computing. So the other thing, main memory is so expensive, and CPU is also so expensive. How much did the mainframe cost at the time? Do you remember? How much did computers cost back in the 60s? About 200,000. And how much does a mini computer cost? About 20,000. And how much does a microcomputer approximately cost? That's a microcomputer, give or take 1,000. So remember, if you're asked to compare sometimes there is the question in the exam that says, what's the difference between mainframes, mini computers, or microcomputers? And you need to know, at least you say this one is more expensive than this one. It'd be nice to say approximately 220,000 and 1,000. That's a microcomputer, we'll assume it costs around 1,000. When they actually came out in the 70s, that's what they did cost. They sold them for 1,000. For the first time, they were able to sell a computer under $1,000. But, okay, so we just take it as an approximate figure. But you need to know those 3 computers. Mainframe, you compare prices, number of users, the power, the power of processing. Okay, so the point is, because things are so expensive, it's not efficient or cost effective to run one program. So they decided we have to run many programs at the same time. So in fact, computers, mainframes can run maybe 100 processes simultaneously at the same time. And how come? How come that there's only one CPU and yet we can run 100 programs? Any idea? Anybody knows? Yeah? Yeah, because of two things. First, programs are not all CPU users all the time. Not every program uses the CPU all the time. Some of them actually use the CPU less than 10% of the time or 5% of the time it runs. Remember, the CPU bound and the IO bound program. So most programs don't need the CPU continuously. So we can give the CPU to one program. It will voluntarily, it will by itself say, okay, I need an input or output. Like it gives up the CPU, say, I don't need the CPU now until I read some information that I can process. So it actually stops using the CPU. So we take the CPU, the operating system, or the processor manager, we take the CPU, give it to the next program. There's only one program most of the time that's actually executing instructions. The rest of them are just sitting waiting, either waiting on a CPU or waiting on input and output. We'll see more details, but I want you to always have the overall idea, so when we talk about something, you know what's happening, what's going on. Now, let's get back to memory today. So today we're talking about the memory manager. So the memory manager allows many processes or programs to execute simultaneously. And there is a requirement that the program, this requirement has been on since with the first computer they had, you must load all the program code into main memory in order to execute it. And it will execute so fast, but it needs to be uploaded. Now, imagine this is memory. I don't know if you can see it. Okay, imagine this is memory. And memory, we said, just a number, millions of switches. And every switch, they group together in a group, and we call them bytes. So every 8 switches stay together, and they're referred to as a byte. And the bytes are numbered. So byte number 0, byte number 1, 2, 3, all the way to whatever you have. Maybe you have 16 billion bytes, or whatever number of bytes you have in memory. And they need to be numbered. And anytime we issue an instruction, or we say, bring me the next line of code, the CPU will give you the exact address. So say maybe we're at location 12 million. Don't get me that line. You get it. The next one is going to be 12 million and 4, 12 million and 8. Get me the next line, and so on. And also, when the CPU needs to bring information, or when a program says, put this information in memory, it also needs to give you the address. So information is moved in memory in something called data bus. So how do you actually move the instruction from memory to the CPU, or vice versa, or you move any data from between different devices, or sending it to the hard disk, or reading from the hard disk, or to the printer. Information goes, at least on the motherboard, needs to travel in what's something called data bus. Data bus, just like a motorway. Like, for example, one of the supermarkets wants to deliver food somewhere, so it might send 10 trucks or 8 trucks, or maybe they only have 1 truck, but they still need to send the same amount. So that 1 truck might have to go and come back few trips. But if you had 4 trucks, they can all go. And if the motorway has 4 lanes, they can all travel simultaneously. So this is exactly what the data bus is like. It's a number of wires that put together that can connect the CPU, memory, and other important, sources or destinations of data. It's called the data bus. And when you buy a laptop, or a computer, as well as whatever the CPU speed is, they'll also tell you this is a 16 or 8 or 32. Your laptop is probably 32 or 64. That's what they're talking about, the data bus. How many bits can you send at the same time, simultaneously? So if you're copying a file from one place to another or sending a file to a hard disk, and the file is big, you read it from one, for example, you're copying a file. You need to read some information from the hard disk into memory and send it to another file. This information is moving around in a data bus. So if your data bus is only 8 bits, you're going to be reading 8 bits each time from that file. If it's 16, it's going to be reading 16 bits. It's going to be moving more depending on the width of the data bus. So when you buy a laptop, always find out how big is the data bus. Like if you had 2 laptops and you have a choice, get the one that's 32 rather than the 16, or get the 64 rather than the 32. And now they're probably, the standard one is probably either 64 or 128. So that will speed things up. So you need a fast CPU, but as well as the CPU, might say, okay, move data, and the slowness comes from the data bus, not from. Now, also, when you say move this byte or this information to memory, you need also the CPU or the program will also give you the address where to put that information in memory. Remember, all memory we said is numbered. 0, 1, 2, 3. So if it tells you to move information into 12,460 location, that's a particular byte. So we want you to put the information here, not before, if not after. So precise. How is the address expressed? How is it written? How is it translated? It's also translated into another bus, and it's called the address bus. So every computer motherboard will have 2 kind of buses. And a bus is just like a ribbon of wires, a group of wires put together, like a motorway. So also the the address bus can be 8-bit or 16-bit or 32-bit. If you had an 8-bit, the biggest number you can write is probably, 256. So the bigger the data bus, the more numbers you can write on it. It's like in a street there are many houses, and they give you kind of a plate like this, and they say, can you write your house number on it? And the numbers have certain size, so you can only write 2 numbers on this plate. That's all the plate allows you. So you can write house number 00, 01, or 38, or something like that. 2 digits, no more. What if you have a house number 100 that needs 3 digits? You can't write it. You can't write that number on this plate. Same with computers. Remember, every order, every command you give to a memory, either to put something in it or go and read something from it, from memory, you must give the exact location where you want to read from or put some information into. Where do you put the exact address? You put it in the address bus. Now, the address bus always has a limit. It's either, again, when you buy a computer, then this is something that does not change. That's it. Once you buy a computer, it has an 8-bit or 16-bit or 32 or 64 or 128 address bus. That means you have a maximum number you can't address anymore. So even if you had more memory, so sometimes the problem is not just not having enough memory. Sometimes you can have more memory into your machine, but you cannot use it. Why? Because your address bus cannot actually write any bigger addresses than a certain address. So only up to this point, it can be addressed. The rest of it, it's useless having it on your computer. So I just want you to know the idea of those 2 buses. One to carry data, transfer data from one place to another. The wider, the better. The quicker data will go. The address bar or the address bus, its function is to pinpoint each individual location in memory. And also it needs to be big enough to address that it can address every point in memory. So if you have more memory than this bus bar or the address bar bus can address, well, then it's not going to be used. Okay, so just keep this information in mind. Now, memory is so important that every program that needs to be executed needs to be placed in memory. And the first and main programs that need to be executed are the operating systems programs. And the operating system, once you switch the computer on, remember, this memory is RAM, is known as RAM, random access memory. And any time you switch the computer off, it loses all its content. Are you looking for a pen or something? Okay. So it's volatile memory, which means when you switch power off, all the switches are switched off. There's nothing, all information is lost. There's no information in there. So when we switch the computer back on, we need to have the operating system there in memory in order for it to execute. Because remember, the operating system is just more software, more programs, more processes that need to run to manage these resources. And in order for them to run, they need to be put into memory. And they are not in memory at that time. So who is going to be running when you switch the computer on to bring the operating system upward into memory? Anybody knows? Yeah? How do we load the kernel? The kernel is actually the operating system software. Yeah. So there's a program in ROM. There's another small chip in every computer. It's called read-only memory. And it has a program, and it doesn't change. Those switches in the ROM, the read-only memory, there's a program in it, and it never switches off. It's burnt, kind of. It doesn't go on and off. And it's done by the manufacturer. And when you switch the computer on, that program will run first. And it normally performs memory test and devices, basic devices like the keyboard. You see the little lights on the keyboard flash when you switch your computer on. So they're tested. Every keyboard is tested there, every key in the keyboard, and every byte or every switch in memory is tested. And if everything is okay, it will go to the hard disk and bring the operating system. And that's the end of this program. So there's a program on every computer, and if it's not there, then the computer will never start. So that program is already there, and it's designed to start working at the beginning. And all its main job really is to go to bring the operating system and put it in memory. Once the operating system goes in memory, it takes control of the machine. You don't need that ROM again until we switch off and switch on again. Okay, but that's where the operating system is loaded. So in every computer machine, the top part of it is allocated to the operating system. And we don't want any other program to go near that area. So every operating system, once it's fully loaded, it checks how big am I, how big is my software, and takes all the memory it needs, and we try to keep it small. And operating systems are so large, they could fill the full memory, but we don't want them to do. That's why we have a kernel. That's why we say only bring the important applications that you need to manage. If there is a function that you do, but you don't need it now while the computer is running, for example, you want to format a hard disk, you'll probably do that once a year. So there's no need to have the software, the process that actually does the formatting until we need it. So we leave that outside. That's not part of the kernel. The kernel are all those parts that manage memory, that manage the devices, that manage files that we are using all the time. Anytime we run programs, they're using files, we're using devices. So the minimum is the essential. But there are some functions that are not part of the minimum part or essential part, so we don't upload them. They're still part of the operating system, but they sit there on the hard disk. Anytime we need formatting, we go and bring that program that does the formatting. When it finishes, gets rid of it again. It doesn't always stay in main memory. But memory manager, it's always there in main memory if the computer is running. Now, the operating system will notice what address have we reached. What's the maximum address that it actually now, it has all its software in. For example, from 0, let's say, till 16 million or 20 million. Let's say 20 million byte. That address there, that's the end, that's the last part of our operating system programs. After that, we can say the users now can use the rest of the memory. So first thing, when that computer is switched on, there's a program in RAM that goes and uploads the operating system. Operating system has to be uploaded, and it actually takes over the machine, and it notices that address that marks the end of the operating system in memory. Now, other user programs can run. So the way they run is that every time a user double clicks and say execute this program, the request goes to the operating system. The operating system says, oh, we have a new process or a new program to be executed. It calls the processor manager, calls memory manager, and say, come on guys, here's a new process one. Just like a new student about to register in college, they probably have, registration office, whatever, office, library, they call them, so they start the processing. Now, we just talk about the memory manager today. So in the old days, this is the way they've done this. They say, all right, they look at a program. Let's say here's a program that needs to be executed. And so the operating system will say, how big is this program? Let's say 150K, 150,000 bytes, maybe. It doesn't matter now what the numbers are. But the total size of a program. And a program needs code in memory, needs a small area in memory for its variables. So every time you say x equals 0, x is a variable. We call it data. So we also give you space for your code, space for your data, and space for something else called the stack. We'll talk about it maybe another time. It's not really important to us now. But the point is, you're getting space there. Let's say this is program number 1. So program number 1 or process number 1 is put in there and a size 150 kilobytes, starting from location 20 million to 20,150,000. Right? So we know exactly where the end, for example, of program number 1. So all this here belongs to program number 1. And most of the time, the operating system will have a table that has a number of columns, information. So it keeps an eye on every piece of program that's there. So it probably says, okay, program number 1 starts at this location and it's running and all that. So these are and then if another program comes in, it's probably given another space in memory. So operating systems will always know where each program is. Program number 1 is in that space of memory. Program number 2 is in this space of memory. And if program number 2 is running, it's allowed to change its own memory. Let's say the code is here and its data is here. It can say, okay, change my variable x into 5 or put 5 or 0 into it. Or perform this x plus y and put the result in n. And n is also in its data area. So every program can manage and change its own data area. But if this program, say, remember every time we say, put this in variable x or y, it's translated into an address. The operating system says, okay, give me the address of that thing. If the address, for example, between 12,460 and 30,000, they say, okay, that's program number 2, that's okay. But if program number 2 give us something to change, in memory address translates into address 10,000 or 10 million, hold on, 10 million is in that top area between 0 and 20 million that belongs to the operating system. Whoa, this program number 2 is trying to modify something in the operating system area, terminate this program. So if a program tries to change or access or do something to another memory location that's not allocated to it, whether it's, of course, this program number 2 cannot change anything in memory area that belongs to program number 1. That's violation. So it's part of the function of a memory manager is to make sure to protect each program from other programs. But no program is allowed to make any change into another area that's allocated to another program. And what's worse, it's not allowed to change anything that belongs to the operating system. It's like, you go to the government there, you try to change a minister or something like that, or change regulations or rules or whatever it is. So that's really the management of the whole system, the memory system. You cannot go near it. So if any program tries to modify any other area, how does the operating system, how does the memory manager know, hey, this is the wrong address for you? Because, very simple, in its table, so we look how it does it. It knows program number 2 starts at this address and it ends at this address. In fact, it only needs the starting address and how big it is. Because how big is a program starting at this point, you add the size of it, then you know the maximum location. So every instruction to change memory is translated into an address. You want to put this value in this address? Oh, if the address comes between the starting point and the maximum point, yes, okay, no problem, you can do it. That's why every request has to go to the memory manager. Your program cannot directly go and change memory. Yeah, you can issue the request, but the request goes to memory manager first, and it will okay it or refuse it. And if you're trying to modify area or memory that belongs to another program or to the operating system, your program will be terminated.